Okay. Thank you very much. I'm Curneyt Akçora. I'm an assistant professor of computer science, and I am also affiliated with the statistics department through my PhD student. So in this talk, I'm going to talk about topology in graph machine learning mostly. And in the beginning, I will speak a bit slower so that you can catch on to my accent, and it will be easier for you going forward. So we have 3 days, and I have divided my content into 3 parts. In the first part, that is today, we are going to talk about topological data analysis. What is it? And I will introduce the language of TDA. This talk is being presented at a mathematical institute at the University of Sevilla in Spain. However, I thought that it would be better to prepare a talk where the terms are easier and more approachable for a general audience. So if you are an undergraduate student, let's say in computer science, mathematics, or statistics, you will have no difficulty, because whenever I have some arcane, obscure terminology, I will always explain it. And for this reason, in the beginning, the slides are a bit full of text, which is not my style, but I wanted to explain the math terms in detail, because most of the time when we work with topological data analysis, the writing is coming from mathematicians, and it is quite difficult to understand. After giving the language of TDA, I will talk about persistent homology in TDA, which is one of the main directions in TDA. I will talk about what is homology, what is persistent homology, and then I will talk about vectorizations of persistent homology. In the second day, I will talk about how we apply TDA to graphs, and I will present 2 of our work, one on Ethereum and one on Bitcoin. In the third day, we will talk about how we can scale TDA so that we can work on very large graphs. Because one limitation of TDA currently is that it cannot work on very, very big graphs. And from that, I will also talk about our new work on Bitcoin, where we create address embeddings for the entire Bitcoin blockchain. So I hope these topics will be useful to you. Topological data analysis. Let's talk about what it is first. So in this section, my aim is to introduce the main concepts of TDA before I introduce the terminology. This is kind of like a top-down approach where I will talk about what is TDA, why we need it, and then we will go into formal definitions. Consider this data point cloud. In this screen, how many, maybe 15 data points exist on 2 dimensions, let's say horizontal and vertical dimensions. And if I ask you what is the true shape of this data, what data generating process may have produced this data? Take a second and tell me what you see. I mean, not tell, but of course, consider what you see in this data. The data comes from a donut-shaped distribution. In a sense, we will not have data points in the center. If we use this data generating process in the future, we are more likely to get new data points that are between these 2 lines, and maybe not outside that much, but the center will be always void. There will not be any data. So in most cases in computer science, statistics, and mathematicians, we have these assumptions that the data is coming from a normal distribution, data is coming from a Poisson distribution, and most of these assumptions are nice in the sense that we expect data to have a shape. However, when data is like this, our statistical tools to describe data don't really work. Consider this new next example. Here I'm showing you a figure, a collection of data sets produced artificially. In this figure, we have the top and bottom panels, and we have 6 panels. As you can see, they are created by different data generating processes. For example, in this one here, And this one here, we have a circle. Here we have a star. Here we have something like a star as well. Here we have parallel lines. But the interesting point is that if you take the summary statistics of them, meaning that if you compute the mean of the data points, if you compute the standard deviation and the Pearson's correlations, all of these figures are the same in summary statistics. So existing summary statistics cannot really distinguish these data points. And why do we need to distinguish different data point generating processes? It's important because we are going to build classifiers that, for example, can distinguish stars from circles. But if our summary statistics are not helping, then our classifier will also not be able to distinguish a star from a circle. And this is a problem. Topological data analysis is driven by the belief that the topology and geometry of the data offer a robust approach to extracting qualitative and sometimes quantitative information about the underlying structure of data. Here, what we mean is that TDA is trying to establish mathematically rigorous statistical and algorithmic methods for inferring, analyzing, and leveraging the topological and geometric structures present in the data. And data, in most of these cases, is represented as a point cloud in a Euclidean or a more general metric space. So by point cloud, I mean something like the figure shown in the middle here. Here you have points. We have not really put them into a coordinate system, but if we put them into a coordinate system like the pot shown on the right, we have 3 coordinates, let's say. The first coordinate is this one, the second one is this one, and the third one is this one. So this pot is represented in the 3-dimensional space, R3. Euclidean space that we used here is a mathematical concept that represents a geometric space with a fixed number of dimensions. For example, here, the pot is represented in 3 dimensions. You could not represent the pot in 2 dimensions because then you will lose the depth of the pot. I mean, if you take a 2D figure like I'm showing here, actually, you can get a 2D picture, but then you will lose the depth information. Here in the pot, you will notice that it is also consisting of data points, like these dots, for example, and each dot has a red, green, blue value. That is why we see it in color. We could represent the same thing in gray, so each dot would have the gray value, let's say, and it would look something similar to this point cloud on the left. Here in this sentence, we mention it's an Euclidean space, or more generally, a metric space. So what do we mean by this? Let's look at the metric spaces. So this paragraph here is copied from the previous slide, and here I'm describing what is a metric space. A metric space M rho is a set M with a function defined on it that takes 2 data points, let's say 2 elements from the set, and maps them into a positive real value. And this positive real value is called a distance. It doesn't have to be called a distance. You could also say this is similarity, or this is dissimilarity, or anything. So we call it a distance because we have designed the function to give us a distance to 2 set elements. In this function, for any x, y, and z, these are the elements of the set belonging to this metric space. If the distance between x and y is bigger than or equal to 0, it is bigger than or equal to 0, and the distance is 0 if and only if x is equal to y. That means that if you take the distance of an element, let's say Curneyt is not a good set element, but let's say Curneyt. And if you take the distance of Curneyt with Curneyt, it should be 0 because these 2 things are identical. Okay. And the second condition says if you are given 2 elements x and y, the distance between x and y should be equal to the distance between y and x. This is actually quite a standard terminology. I'm describing this not for math students, let's say, but for general audience. So in a sense, It does not matter if it is x and y or y to x, the distance is symmetric. In the third condition, it says the distance between x and z is less than or equal to the distance between x and y plus y and z. So this is something that we know from geometry, okay, in general. And geometry is usually defined on the Euclidean space, so you can kind of understand where we got all these notions in high school. Okay, so here is the general process of TDA. Before I go into detail and explain homology, persistent homology, and all this, I'm going to give you an overview about what we are doing in TDA. In TDA, in traditional TDA, which is a tool of mathematicians actually to do data science. Why is TDA becoming popular in these days? Because it's a way of mathematicians to do data science compared to computer scientists' way of doing data science. This depends on rigorously defined mathematical concepts. In a sense, we like TDA more because of that. So in the process, you are usually given some input data, and the input data is considered to be a finite collection of points. That means that there is a limited number of items in your data, number of data points in your data. And furthermore, there exists a measure of distance or similarity between these points. So you can define a similarity measure on your elements. The distance can be determined by the metric of the surrounding space, such as the Euclidean metric. If the data is embedded R&D, you can use the Euclidean metric. Otherwise, you can define a pairwise distance matrix intrinsic to the data. That means if your data points are so strange that you cannot use the Euclidean space, you can perhaps use some other similarity metric. What can it be? For example, if you are given a set of categorical values like city names, for example, maybe you can define a distance on them that follows the matrix definition. How you can do this? Well, it's difficult, but maybe you can find a way. So the specification of the metric for the data is typically provided as an input, or it is guided by the specific application. It is crucial to know that the choice of metrics plays a significant role in uncovering the topological and geometric characteristics of the data. So what this is saying is that distance, defining the distance and using the correct distance is crucial. If you want to get something out of TDA, you need to have a well-defined distance. Now, the second step is that by using this distance on the data points, you construct a continuous shape and emphasize the underlying topology or geometry of the data. In simple terms, that means I'm going to give you this pot as individual pixels, and by looking at the pixels, you will create a continuous shape, and then from this shape, you will say, aha, this looks like a pot. We are all human beings, and when we look at this picture, we kind of see that there is a pot. The main point is getting the computer to understand this is a pot. In 2D, once we have this shape is typically a simplicial complex. And a sequence of nested simplicial complexes known as a filtration. Here, I am showing you just one simplicial complex. If we have multiple of them, it's called a filtration. And I will show you how we compute this filtration. So let's look at this simplicial complex. In this simplicial complex, we will have some simplexes, which I will cover shortly. For example, this simplex here is a 2-simplex because it includes 3 elements. So this, for example, edge that connects 2 data points is called a 1-simplex and so on. I will talk about this in a second. But the main idea is that we are going to use these simplexes as building blocks to create a simplicial complex. Now, once you create a simplicial complex, let's say this is your data point in the beginning, you create some distance, you compute the distances and you create a simplicial complex. Let's say this is the simplicial complex 2, and then you will have this filtration where you create more and more edges between data points, and then you will have a nice filtration at the end, and at the end, everything will be connected, let's say, completely connected graph. Every data point is connected to every other. So this idea of taking your data and then creating edges and then creating simplexes, creating a simplicial complex out of this, and then observing this whole process is called a filtration. Okay. In this, this is the main step. So from simplicial complexes, we will compute a filtration. Now, what are these simplicial complexes? Simplicial complexes are actually higher dimensional extensions of neighborhood graphs. In this figure here, I am showing you a graph. So what is the difference between a graph and a simplicial complex is that in simplicial complex, we will consider some of the subgraphs as just one element. For example, here, this means this is considered one element. So instead of creating a graph out of nodes and edges, we are actually going to have a graph where we have nodes and edges. For example, this node here, we have this edge between two nodes, like ordinary graphs, but we are going to also have some higher dimensional simplices. These simplices, you can consider them as higher dimensional things. And these days, for example, using simplicial complexes and using hypergraphs are two main approaches for higher dimensional graphs. And simplicial complexes are a very popular way, actually, of looking at the graph. In the hypergraph on the right here, what we do is we define an edge that connects multiple nodes at the same time. So here, for example, these black dots are nodes. In the original graph, we had edges that were connecting individual nodes. In the hypergraph, we have an edge that connects how many? For example, here we have 1, 2, 3, 4, 5 edges connected by this light orange looking edge. So in the hypergraph, we have edges that can connect multiple nodes. This is the definition of a hypergraph. Yeah. So once we define these simplexes, then we can have some meaningful information about the data structure. And this data, this information can be used in practical applications. This is the D of the second step. Now, the third step is that the structures constructed on the data, they provide a means to extract topological or geometric information. So it may involve generating rough summaries or approximations that require specific methods, such as persistent homology, to extract relevant information. Persistent homology is the main topic of today, but before we go into this, let's consider these rough summaries. So what this sentence is doing, that once we have the simplicial complex, we have 1, 2, 3, 4, 5, 6 simplicial complexes, and the combination of them is what we call a filtration. So at each step, we actually have a simplicial complex. And in this simplicial complex, we are going to use persistent homology. But let's look at it from a layman perspective. What do you see in this filtration? Look at here. In this filtration, for example, in the second one, you can see that most of the data points are not yet connected. Some of them are connected, but not much. And when you look at here, how many connected components there are? By connected component, I mean these shapes where edges connect one node to the other through a path. So this is my first connected component. This is my, for example, second connected component, third, fourth, fifth, and so on, right? So there are more than, let's say, 5 connected components here. If I go from the second step to the third step, as you can see, the number of connected components is reduced to just 1 here, because you can reach this vertex from any other vertex in the data. And by vertex, I will use the vertex and node interchangeably. So vertex and node are the same thing, almost the same thing in computer science. Vertex is something that the physicists use in network science, and node is something that computer scientists use. So in this third filtration, you will see that now we have just a single connected component. So this filtration already gives me some information that beyond the second step, everything will be connected almost. But even here, we see some shapes. For example, it seems like there is a hole in the data here, for example. And if you look at the original data point cloud, you could also see the hole here. Then you have another hole here, which was the hole here. Then you will have another hole in the first one, another hole here, another hole here. But as you can see, this hole here is the biggest hole. So this hole is going to persist a little bit. And if you look at the fourth filtration, the hole is still here, the bigger hole, and the smaller ones, they are closed in the fifth simplicial complex, but you see the biggest hole is still here. So this is important information. In a sense, if you are looking at it from a data point perspective, why do we have a hole here? Why don't we have data points in this hole like this so that there would not be a hole? So what is the point for this hole to exist? That is some information that we need to understand. And filtration gives us this information. Any questions so far? Rocio, if there are any questions, please ask immediately. Okay. So once we have this filtration, once we extract some rough summaries or we extract something from persistent homology, then we kind of have a novel sets of features and descriptors for data. Here, what we mean is that this novel set of features means some values that represent the graph, data point. For example, we can say how many connected components were there, what else? How many edges formed between data points and so on. Descriptor, also we call invariant for this as well. Descriptor means that is something that gives an idea about the whole data set. So that is the descriptor. For example, we can say that the data looked like a ball, which actually was the case. If you look at here, the data looks like a ball. The data could have looked like a triangle as well. So this is the kind of descriptor we are talking about. These features can enhance the understanding of data, especially through visualization techniques. They can be combined with other types of features for more comprehensive analysis, and they may also facilitate machine learning tasks. One common theme in topological data analysis is that topological data analysis may bring additional features or descriptors that you would not be able to extract by using traditional computer science methods. So TDA can be complementary information in your classifiers in machine learning. Furthermore, the information provided by TDA can be utilized to design data analysis and machine learning models that are suited to the characteristics of the data. So one common thing we do in our research is that we need to demonstrate that TDA brings additional value compared to other features computed by, let's say, traditional computer science approaches. Understanding how the extracted information complements existing features and showcases its advantages is a key aspect of this process. Okay, so these were the 4 main points of TDA. We were defining a distance and the metric space on the data in the first step. In the second step, we were creating simplicial complexes. In the third step, we were doing filtration over simplicial complexes. In the fourth step, we were extracting rough summaries or descriptors from each simplicial complex by using TDA. I hope I did not lose you yet. So in this section now, we are going to go into the language of TDA, and my goal is to familiarize you with basic words and concepts. So let's look at first simplicial complexes. We talked about them. So simplicial complexes are extensions of graphs to higher dimensions. They are mathematical entities that possess both topological and combinatorial characteristics. And what do we mean by this? By topological characteristic, we mean that simplicial complexes have a topological nature, meaning they capture information about the connectivity and spatial relationships within their constituent simplices. So what this is saying that there are simplexes of different types, and simplicial complex connect them and gives us a special relationship, and this is the topological characteristic. Simplicial complexes provide a framework to study topological properties such as connectedness, boundaries, holes, and other dimensional structures. I have not shown you what these mean yet, so don't worry about this. We are coming to that in a second. The second characteristic of simplicial complexes is the combinatorial characteristic. Simplicial complexes have combinatorial properties which deal with the arrangements and relationships between their simplices. That means by looking at the simplicial complexes, we can see how the simplices are combined. What I mean is that here is a simplex that is an edge, here is another edge, and they are connected. And then this edge is connected to a tetrahedron, I believe, yes, through this node. So this kind of connection, the combinations, are studied as combinatorial characteristics. Yeah. What we need to know next is how we define a simplicial complex or simplexes. We define them by using simplices. Given a set X that has elements from 0 to k, that means there are k plus 1 elements in that, and they are d-dimensional. Remember, in the teapot example, we were looking at a data point in 3 dimensions, so that means d can be anything here. We are not specifically saying it is 2 or 3 or anything. We will just use d for it. So in this set, these x0 to xk are affinely independent points. Okay, and by affinely independent, we mean that these are a set of points in a vector space that do not lie on the same affine subspace, except the case when the set just contains one point that we cannot do anything. There is just one element in the set. In other words, a set of points 0 to xn is said to be independent affinely if there is no non-trivial linear combination of the data points that results in the 0 vector. So that means there is no easy way to just subtract or add the vectors to get 0, except when all the coefficients are 0. And that, further explained, means that we have a set of data points that are not in a straight line or a flat plane. So we have kind of data points that are interesting. That is the whole thing. Now, in these points, the k-dimensional simplex spanned by x can be defined as the convex hull of x. So in this sentence, you may not know what do we mean by the convex hull of x. And the next slide is about this. So here in the bottom, I am showing you a set of data points. The convex hull of a set of points is the smallest convex shape or region that completely encloses all the points. So in the figure B here, we see the convex hull of this set of data points. If we had another point here, the convex hull would be extended to cover this as well. Mathematically, an n-dimensional simplex is defined as the convex hull of n plus 1 affinely independent points in n-dimensional space. In other words, it is the smallest shape that contains these points. So I will show you two things. Let's say we are looking at this data point that is the only data point in your set. If you look at this definition, this is a 0 simplex. 0 simplex. If you have two data points here and you connect them through an edge, this is the convex hull. This is the one simplex. One simplex. And then the more interesting thing is, of course, not 0 simplex or 1 simplex, higher simplicity. If you have 3 data points as shown here, how can you create the convex hull? Well, basically, this looks like a triangle. So this is the convex hull. This is now a 2 simplex. Okay. If you have more data points, let's say 4, and then you will have this convex hull and so on. Okay. This is the main idea. So n-dimensional simplex is defined as the convex hull of n plus 1 affinely independent points in n-dimensional space. Why, for example, in this edge case, why don't we call it a 2 simplex? Why do we call it a 1 simplex? Because if you think about it, these two data points, if they are on a line, we need just one dimension, let's say the horizontal dimension or the x dimension, to capture the location of this. For example, this data point here can be at horizontal index 1, and this can be at horizontal index 3. So we just need one-dimensional space to represent two data points. We need two-dimensional space to represent 3 points, and so on. Okay. So an n-dimensional simplex is defined as the convex hull of n plus 1 affinely independent points. It's okay. So a one-dimensional simplex is a line segment here. This is actually the convex hull of 2 points. But the convex hull just includes these data points and the edge between them. 2 simplex is interesting because it now has an area that we can visualize. A 3 simplex is interesting because it has an area that we can visualize, and so on. So this is the idea of a simplex. Yeah. Going from simplexes to simplicial complexes. A geometric simplicial complex K in d-dimensional space is a collection of simplexes satisfying the following conditions. Every face of a simplex in the simplicial complex is also a simplex. The intersection of any two simplexes in K is either empty or a common face shared by both simplexes. So in this description, you may not know what is a face. The face of a simplex refers to a lower dimensional simplex that's a subset of the original simplex. In other words, it's a subset of the vertices of the simplex that defines a smaller simplex within it. I think the next example will be nice because here we have a tetrahedron. A tetrahedron is basically a 3 simplex. But in this tetrahedron, what we have is we have these faces because there are 4 data points, the first point, the second point, the third point, and the fourth point. And each triple is connected in a 2 simplex. So for example, this face is a 2 simplex, this face is a 2 simplex, this face is a 2 simplex. There's another face on the other side that we don't see, it's a 2 simplex as well. And this 3 simplex is created by 4 faces. 4 faces, 4 vertices, and 6 edges. So the edge here is actually the edge that connects this, for example, first face with the second face. So this is the intersection, this point is the edge. So you can take, let's say, 5 simplex and find its 4 simplexes. You can take a 4 simplex, find its 3 simplexes, and you can deconstruct them down to 0 simplexes. Okay. Why? Because vertices were 0 simplexes and edges were 1 simplexes. So you can continue down and deconstruct them into smaller pieces. Yeah. So once we have simplexes in a simplicial complex, we say that we have an underlying space of K which inherits the topology of the d-dimensional data point clouds. So this is saying that we had a data point cloud in the beginning in d dimensions, and now we create a simplicial complex out of it. And this simplicial complex will give us the underlying space. So the simplicial complex is a topological space based on its underlying space. And what do we mean by this underlying space here? What we mean is that when we say that a simplicial complex can be regarded as a topological space based on its underlying space, we mean that we can associate a topological structure to K. by considering the topology inherited from its underlying space. That's like saying that we construct a pod out of the data point cloud that looks like pod. Okay. It is worth noting that once the vertices of the simplicial complex are determined, the combinatorial description of the collection of simplexes adhering to certain incidence rules fully characterizes K. What that means is that once we have the simplicial complex, based on the simplexes on it and how they are connected, we can fully characterize the simplicial complex. So that means given two different simplicial complexes, we can distinguish these two things, these two simplicial complexes. I hope that was not very abstract. Okay. So consider that so far I have been talking about topological data analysis on point cloud data, which is actually not our topic, because our topic is topological data analysis on networks, on graphs. But even here, you can see how the graph terms have already creeped in. We are talking about nodes, we are talking about edges, triangles, and so on. So you can see the affinity between topological data analysis and graphs already, because what TDA is doing on point cloud data is basically creating a graph out of it. But unlike traditional graphs where we have just nodes and edges, in that graph created by TDA, we also have simplexes. So I always tell this. In a traditional graph, let's say you have these nodes and edges and there are some shapes. And what happens if some of the nodes are not nodes, but let's say diamonds here? Okay, so here is a diamond for you, or diamonds would be something like this, right? Okay, so instead of a node, you have a diamond. And then there is another diamond here that is connected to the first diamond. And then they are connected to a node, and then so on. This is basically a simplicial complex. It is not that far away from a traditional graph. This is what we are trying to reach here. We are trying to create this from our data point cloud. And this, once we create it, looks just like a graph. Okay. Yeah. Good. Now let's move on.
So, you say that you only consider zero-dimensional topology, because TDA on graph is this. I don't have the meaning. I don't understood the meaning. TDA on graph, you mean only zero-dimensional topology? You compute only zero-dimensional topology, or is a way to say that you are generalizing graphs?
What I mean is that we are going to generalize topological data analysis so that it works on graphs, not only on data point clouds.
Ah, okay. Got it. Thank you.
Yes. But what I mean in this slide is that even before we think about how TDA can be applied to graphs, what we create is very similar to graphs. Even on typical traditional point cloud data, TDA looks like graph analysis already. Okay. Yeah.
Okay, thank you.
Yeah, you're welcome. So we talked about simplexes, we talked about simplicial complexes, and I mentioned that if we have multiple simplicial complexes in a succession, that creates a filtration. Okay, and then on that filtration, we are going to compute something called persistent homology. These were the first 4 steps of TDA. Now, how do we compute simplicial complexes actually? Like, we have the data points in a point cloud, and I was just adding edges between them. But how do you add the edges between them? What is the procedure there? So there exist many ways actually to build simplicial complexes. There are many ways to define distances, and once you define the distances, there are many ways to build simplicial complexes. I will present a few classical examples. An initial example, let's say you have a point cloud data, and the data looks like this. There are 5 points. you can say, when I'm creating the simplicial complex, what I can do is I can connect each data point to the other if the distance between two data points is less than, let's say, an amount x. Okay, so in a sense, we are doing something with distance. This is the first idea, and this first idea is called a Vietoris-Rips complex. And for this distance, remember we had a distance function that was taking two data points, x1 and x2. We will use alpha for this threshold. So if this distance is less than, let's say, alpha instead of x here, we will say I'm going to create an edge between these two data points. The Vietoris-Rips complex, which we will denote as Rips of x at alpha, consists of simplexes x0 to xk. That means there will be k plus 1 data points in it. And satisfying the condition that the distance between any pair of points is less than or equal to alpha. So that means this should be less than or equal. So if the distance is less than this, we are going to create an edge. And let's say the alpha is 0.5, and really the distance between these two data points were alpha 0.5. But if you consider this distance is much bigger than 0.5, and we do not create an edge yet for these two data points. Of course, mathematicians have better terminology than saying this or that, so they use what is called a closed ball. So in this figure, I am showing a data point cloud in 2 dimensions. Here is the first dimension horizontal, and here is the second dimension vertical. Okay, and as you can see, how many data points there are? This is a data point, this is a data point, 1, 2, 3, 4. There are many data points. And you can think of it as the nucleus of an atom. So the nucleus is the data point, and here we have a closed ball. The closed ball is showing you the distance from the data point. Okay, so this radius here, let's say this is this radius, this is the distance. And we define one distance, let's say R1, and then we create these balls around every data point. And if two data points have intersecting balls, like for example, look at this intersection between these two data points, x1 and let's say x2. They have an intersection. So if they have an intersection, we create an edge between them. Okay, this is the main idea in Vietoris-Rips. This is very similar to looking at your neighbor and then connecting with the closest neighbor. In this case, for example, let's say alpha is 0.5, and this data point at the bottom right is quite far from everything. So with this alpha, its closed ball is not intersecting with anything. For this reason, this data point yet has no edge to any other data point in the point cloud. We would need to extend this until here to create an edge. So we need to increase alpha for this data point specifically for it to create an edge. When you look at this figure, one thing will draw your attention. Some of these shapes are shaded and some of them are not shaded. So what is going on here? So what is going on is that here, let's say this triangle here has 3 data points, 1, 2, and 3. And the distance between 1 and 3 is less than alpha. The distance between 2 and 3 is less than alpha. And the distance between 1 and 2 is less than alpha. In that case, this shape is called a 2 simplex. So we have created a triangle out of these 3 vertices. This is why it is shaded. More interestingly, here we have 4 vertices with distances less than alpha. This is why here we have a tetrahedron. In this case, this rectangle is not filled. Why? Because the distance between, let's say, I was left at 1, 2, 3. Let me use 4, 5, 6, and 7. You see, the distance between 5 and 6 is less than alpha. 4 to 5 is less than alpha. 4 to 7 is less than alpha. 6 to 7 is less than alpha. But the distance between 5 and 7 is not less than the alpha. It is bigger than alpha. Furthermore, the distance between 4 and 6 is bigger than alpha. For this reason, these 4 vertices are not connected as in this case of tetrahedron. For this reason, this area, let me share another color. Yeah, so this area here is not filled yet because it does not create these 4 vertices, 4 nodes do not create a 3 simplex yet because of these 2 distances. If we increase the distance a little bit, if, for example, 5 and 7 is less than alpha, if 4 and 6 is less than alpha, then it will create a tetrahedron. Okay, good. So one interesting thing is this. In general, even when X is a finite set of RD, and let's remember what was X, the X is your data point cloud, RIPS X at alpha may not have a geometric realization in RD. What do we mean is that it cannot be represented in RD. Why? Because we may have multiple data points. Let's say in 2-dimensional space, you have these 3, 4 data points, and their distances are less than each other. So they create a tetrahedron that is a 3 simplex. But we created this out of 2 dimensions, X and Y. So this simplex has a higher dimension than the original data point cloud. The original data point cloud was in 2 dimensions, and the simplex is in 3 dimensions. This is why we don't have a geometric realization in RD. We will have a geometric realization in this case in RD plus 1. Okay. So the first idea was to use a distance. That is the vector series. That is what everyone is using. That is what we are using because it's easy. Once you have the distances, you can kind of look at if the distance is less than a threshold, you add an edge. The second idea is called a Čech complex. And I have never used Čech complex, but the idea is that it's defined as the set of simplices such that the K plus 1 closed balls have a non-empty intersection. So in this case, we are not looking at the distance specifically, we are looking at K plus 1 will have non-empty intersections. So RIPS is a subset of Čech, and Čech is a subset of RIPS at 2 alpha. Okay. Additionally, if X is a subset of RD, then Čech at alpha and RIPS at 2 alpha share the same 1-dimensional skeleton. And the skeleton of a simplicial complex captures the lower dimensional simplices or building blocks of the complex. What that means is that in the previous figure, for example, we have these simplexes, but if we just look at the one skeleton is just nodes and edges. So we will disregard these triangles and tetrahedrons, and we will just give the nodes and edges. And in Čech and RIPS at 2 alpha, we have the same one skeleton. So the edges and the nodes will be the same in the data point cloud. Okay. Okay, good. So we have made this far. I'm glad to say that we have covered most of the terminology. Okay. So now we will go into some applications. We will look at how TDA is used on graphs. I showed you simplices, first of all, distance and metric, simplices, simplicial complex, and filtration. Okay, and then we talked about how we create simplicial complexes in 2 ways. The first way is via RIPS, where we use a distance threshold to create edges. And the second one is Čech, where we look at K plus 1 closed balls. All fine and nice. However, we can make this simplified classification about topological data analysis. In topological data analysis, we have 2 main directions. The first direction is called a persistent homology. It's called the persistent homology. Persistent homology studies the topological shapes that can fit into your data. In this figure, I am showing you one filtration, and then data points are isolated in the beginning, and then we increase the alpha threshold for the distances, and then some of the edges are nodes are connected, and then some others are connected. Two simplexes are created. This is the triangle here, and then we still have a loop here. So the persistent homology is trying to identify this process and track this loop. For example, this loop is formed here first in K4, and then it also persists in K5. So in a sense, we are trying to find these local shapes in our data. The second direction in topological data analysis is called TDA mapper. TDA mapper is more worried about the overall shape of your data. And both persistent homology and TDA mapper have filtrations and distances. But mapper studies how your entire data is shaped. Mapper is not trying to fit topological shapes into your data. For example, in the right figure, I am showing you a figure created by my PhD student, Mary. We have something that looks like a graph, but actually that's a TDA mapper network where we have nodes and edges, but each node is a cluster of data points from your original data. So, for example, let's say this node here is actually a cluster of data points. So there may be more than one data points in this cluster. How many data points we have here? Well, here I am showing you graphs from graph classification data sets. We have BZR dataset, MUTAC dataset, NCI1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here are graphs from 9 different datasets, more than, let's say, 6,000 to 7,000 graphs. And each cluster contains potentially more than one graph. And TDA mapper is looking at this overall shape. For example, TDA mapper is not trying to find that there is a one-dimensional loop here. It does not care. TDA mapper says this part of the graph, for example, is very far away from this part of the graph. Let's say this is the region 1 and this is region 2. And TDA mapper says, why are they so far away from each other? Is there a meaning? Because when you apply this to biological networks, that means R1 are the healthy people and R2 are the people that have a certain disease. So TDA mapper is was created by Gunnar Carlson, and he built a company out of it. And they are mostly working on biological data, and they have great success there. I have used both persistent homology and TDA mapper in my research. With TDA mapper, I have 3 articles. However, with persistent homology, I have more than, let's say, 10. Other than these 2 main directions, we have some novel ones, for example, cellular sheaves, Euclidean approaches, and so on. In the future, they may also end up as main directions, but not yet, in my opinion. Okay. So one common point, persistent homology and TDA mapper, both of them have filtrations and distances. Yeah. So now I will start talking about persistent homology in topological data analysis. I have around 16, 17 slides. So after, let's say, half an hour, we'll be done with today's lecture. Okay. In this part, my aim is to familiarize you with filtration and persistent features. So what we covered so far, we covered topological data analysis on data point clouds where distances are well defined, for example, Euclidean. We talked about simplexes, simplicial complexes, and filtration. And we looked at how we create a simplicial complex. Now, what do we do once we get a simplicial complex? That is the topic of this section. TDA in a nutshell. We are given X data points in d-dimensional space. We find pairwise distances between data points. We create simplexes, and then we attach simplexes to create a simplicial complex out of them. And then on a simplicial complex, we identify certain topological features. But what are these topological features? We need to first talk about shapes to answer this question. Homology, coming from Greek, homo means the same, and logy means the study. Homology means studying the shape, similar shapes. It's a fundamental concept in algebraic topology that provides a powerful tool for formalizing and analyzing topological features of spaces or simplicial complexes in an algebraic manner. So, homology enables us to capture and quantify the presence of different dimensional holes within a given space. Each dimension k in homology corresponds to a vector space Hk, where the dimension of the vector space represents the number of independent features of that dimension. For example, if you look at zero-dimensional homology group H0, it describes the connected components of the complex. We already seen this. So zero dimension means how many connected components you have. One-dimensional homology group represents the one-dimensional loops or cycles, and the two-dimensional homology group captures the two-dimensional cavities or voids within the space. Now, we talked about simplexes, but now here is something new. Here is what we call a homology group. And the zero simplex and the zero-dimensional homology group are completely different things. Okay, so that is one thing that is actually quite confusing when you are new. Zero simplex is not the same thing as zero-dimensional homology group. Now, homology, I will detail this soon. Homology provides a framework for understanding and characterizing the topological structures by associating vector spaces to each dimension. Okay. In simple terms, we are defining topological structures, for example, k-dimensional holes, and counting them in a simplicial complex. But what are these holes? Now, the term dimensional holes refers to topological features captured by the homology groups of a simplicial complex. These holes represent voids or empty spaces of different dimensions within the data. In a few slides, these will be very clear to you. In the context of TDA, the hole does not really refer to a physical hole, but rather to a topological concept. A dimensional hole can be understood as a region or a subspace of the data that is missing. Okay, so consider the cheese that you buy. Okay, here's a very bad drawing of a cheese. This is your cheese, let's say. And you know, when you slice the cheese, you will find that there is a hole in the cheese, like a bubble here. So this is what we are talking about when we are looking at data. The hole here is, for example, a two-dimensional hole. Okay, and this is a part of the missing data, and we are trying to identify them. Why is there a hole in data? Why the data points here and here are not connected to each other? There may be a reason. Now, what are the holes? Holes can be in any dimensions. For example, there exists a thing called 100-dimensional holes, or 101st dimensional holes, or 102nd dimensional holes, so on. But mostly, we are looking at 0 and 1-dimensional holes. Why? Because they exist. These higher dimensional holes don't really exist in most data. 0-dimensional hole. They are connected components in a simplicial complex. For example, I'm showing you the K1 here. K1 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data points. Okay, and none of them are connected. So each data point is actually isolated. In this case, we say that there are 12 disconnected components or connected components. So K1 has 12 zero-dimensional holes. Next, if I increase the radius in a closed ball, you will see that K2 has larger balls, but there are still 12 holes because data points are still not connected. Next, I increase the balls a little bit more, and you will see that now there are edges. And there is even a 2 simplex here. Look at this interesting thing. We have a triangle here. There's a 2 simplex. And there are 6 zero-dimensional holes. Why? This is the first one, second, third, fourth, fifth, and sixth. So we have 6 different components, 6 zero-dimensional holes. Okay. Let's increase the radius a little bit more, and you will see that now the data point is completely connected, a second 2 simplex appears here. This was the first 2 simplex. This is another 2 simplex. So we have 2 simplexes, and we have nodes and edges. Okay, and here K4 basically, K4 has just one 0-dimensional hole. That means there is just one component in K4. So each one here is a simplicial complex, right? This is the first simplicial complex, this is the second simplicial complex, and this is the fourth simplicial complex. And this, going from left to the right, is what we call a filtration. Yeah. Now, these were the 0-dimensional holes. 1-dimensional holes are loops in a simplicial complex. So we are looking at loops as in graph theory. So let's say you have a graph like this, and here is the connections like this. This is a loop, right? We are looking something like this. 1-dimensional holes are loops in a simplicial complex. K1 does not have any 1-dimensional hole because nothing is even connected yet. We increase the ball, K2 has no 1-dimensional hole. K3 does not have. Why? Because you will see here, these 2 simplex, you will consider this as a loop, but it's not a loop actually, because as soon as the distances are surpassed, this face is shaded. So there is no loop here anymore. This is a shape itself, like a triangle in the graph. If we increase a little bit more, now you see this 1-dimensional loop appearing here. Now we have 1-dimensional hole. These were 0 and 1-dimensional holes. Then there are 2-dimensional holes, 3-dimensional holes, but they are increasingly more difficult to visualize and intuit about. So I will stop at 0 and 1-dimensional holes. Because in personal homology, in most cases, we also look at 0 or 1-dimensional holes. Okay. Now, once we create a simplicial complex, and once we kind of look at these holes, we use Betty numbers to count these holes. So, for example, Betty 0 is the number of connected components at, let's say, alpha or rho equal to 0. So this is this rho, this P here is the alpha parameter that we were using before. We actually are quite consistent. We use either alpha or epsilon. In this case, we use P to mean the distance. Okay, so let's look at these 4 cases. This is the first simplicial complex, second one, third one, and the fourth one. Oh, sorry. In here, I was talking about P being alpha. No, it's not alpha. It's not alpha, sorry. So we are looking at the epsilon distance threshold here, and the P is the dimension of the homology group. I was telling you not to confuse 2 slides ago, and I did myself. So in the first simplicial complex, nothing is connected. Epsilon 1 is 0, and the number of 0-dimensional holes is 20 because there are 20 data points. So the Betty 0 is 20. Betty 1 is 0 and Betty 2 is 0. In the second simplicial complex here, we increase the epsilon a little bit and create some edges, and triangles are filled, but here we have a rectangle here. That is a 1-dimensional hole. This is why the Betty 1 is 1 here. And how many Betty zeros do we have? We have this one, this one, this one, this one, this one, this one, and this one. So 8 total. Do we have 8? Yes, this is the 8th one. Okay, good. In the third simplicial complex, now we have a 1-dimensional hole here. That dimensional hole that we had here is closed, you see, because the distance between diagonals closed. So this became a tetrahedron. There is no longer a 1-dimensional hole, but now there is a big 1-dimensional hole that appeared at the center of the data. Okay, so B1 is 1 again, but these 2 B1s have different holes in them. In the first one, there was this small hole. In the second one, we have this large hole in the center. And if you go forward, now this hole will also close, and Betty 1 will be 0, but this will turn into a 2-dimensional hole. So Beta 0 is reduced to 1 because everything is connected. There is just one connected component. If you look at the subset or equal relationship, this is the relationship between simplicial complexes along the filtration. Okay. Any questions so far? We will see some more examples of this. Okay, good. So here I am showing you another example. On the top left, we have a simplicial complex. In the simplicial complex, we have edges, nodes, and triangles. And then we have a tetrahedron here. So this is the tetrahedron. And from this one, we actually do 3 filtrations. Why do we do 3? We could do more, but let's say 3. This is the first filtration, second filtration, and third filtration. And you can see increasingly now at this point, there is a one-dimensional hole here. Is there another one-dimensional hole anywhere? I think there should be one more. Because looking at the beta 0 and beta 1 here, this is what we call a barcode graph. And on the x-axis, we have the threshold. So at r equal to 0.6, this is our alpha. We always use alpha or epsilon here. So alpha 0.6 around here, there is no one-dimensional hole. Around 0.8, there is one-dimensional hole that is starting. So horizontally, each one is a hole. So this is the first one-dimensional hole. This is the second one-dimensional hole. This hole here is which one? This one here. And this other one here starts at 1.2, so this is big. This is this big hole. However, right now I fail to see where is the hole in this figure on the left. I think they made a mistake. There is no hole here because these triangles are filled. Okay, so barcode is an interesting thing. In barcode, every line represents a different 0-dimensional or 1-dimensional hole. And the x-axis is the distance. So from 0 to 2, for example, you increase the distance and then some of the holes die. For example, in the 0-dimensional case, going from this first simplicial complex to the second simplicial complex, you see that they get connected, so holes die. When they die, they look like this. There is a dead threshold here. We can say this dies around 0. For example, 4. Okay. Yep.
Hello, unit. I think I can see the second hole because it is born just after 0.8. If you see the where you have this arrow you are pointing, imagine if you increase the ball, then you have the new hole between the two triangles. Imagine you increase the ball a little bit, then you have the new hole between this. Yes, there. So
I see.
Yeah.
But in this figure, it does not exist. It exists.
No, it doesn't exist. Right. So it is born later. Yes, maybe 0.85 or something.
Yes. So let's say at 0.8 here there is nothing.
Yeah.
But 0.88, then this hole will be born. Yes, good catch. Good catch. Yeah, thank you. So this is actually quite important. Like understanding how holes appear and disappear in very simple toy examples is very important. In our research work, we usually write the code and do something. At the end of the day, we have some inexplicable behavior, and then we always need to go create a toy example and show how it works in the toy example. And then I always end up putting that figure in the graph in the article as well. So the fundamental things are very important. And thank you for catching this. Yes, this is the one-dimensional hole that would be here. So on this panel on the right, we see the topological invariance. I mentioned that invariant and descriptor is the same thing. Computer scientists use actually invariant, and the mathematicians use descriptor mostly. Okay, so topological invariant, that means if you extend this edge, or if you just move this vertex from here to here, there would still be a loop here. It would not change. Okay, so in this figure on the top, we have how many nodes? 1, 2, 3, 4, 5, 6, 7 nodes. Beta 0 is 1 because in this simplicial complex everything is connected. There is just one connected component. Beta 1 is 1 because of this hole here that is not filled yet, and beta 2 is 0. In the second example here, we have beta 0 again 1. Beta 1 is 1 because of this hole, and beta 2 is 0. And in the third figure, we have beta 0, 1 again, beta 1 is 0, and then we have a two-dimensional hole in a tetrahedron. So there is a two-dimensional hole here. Yeah, good. So this birth and death is actually quite important. And we need to know, like this, for example, one-dimensional hole is born here at this point and dies at this point. And persistent homology looks at how long that takes, because it says, persistent homology says that if a hole just appears and dies immediately, it cannot be an important hole. If a hole appears and stays longer, consider this hole here, that's a long, like large hole, that is more important, and it will persist. So I'm getting a little bit ahead of myself because in the next slide we talk about persistent homology as well. So homology gives you a tracking capability of like seeing which holes persist. So the persistent in the name comes from there. Which holes do not die in a short time. These are the important holes. We can go to like 10-dimensional holes, 11-dimensional holes, and so on. However, in most data points, we don't see bigger than 2-dimensional holes. Okay, and formal definition of the holes depend on homology groups and boundaries and so on. As a computer scientist, I am not inclined to go into that mathematical direction. So if you want to find what is a formal definition, how you can compute it by using, let's say, linear algebra, please check these papers. You will find them. In persistent homology, this algorithm, I gave it before. I said we give the data points, given the data points, we define distances, we create simplices. In persistent homology, we add two new steps, two more steps to TDA. In the third step, instead of just taking the data and counting holes in them, we will use a filtration threshold on distances from 0 to maximum. It doesn't have to be 0. What I mean by 0 is here minimum. So minimum can be -10, for example. We don't know. We create simplices and a simplex complex out of them by using, Selim, remind me that I need to add this, by using epsilon as the distance. So Selim is the teaching assistant. He is here with us as well. I need to say that in this step, we will use alpha, the threshold, to create the simplices. In the next step, we identify topological features. We already talked about this. And we identify which holes persist, which are born and survive, and we record them in what we call the vectorization of the data. So the vectorization will, for example, tell us at point alpha 0.5, here are these dimensional holes, for example, 0-dimensional holes or 1-dimensional holes, and they survive until, let's say, alpha 0.8, and this one survives until 0.9, and so on. So this is the vectorization that can be used in machine learning tasks for classification. Okay, that's the main point. Now, we talked about filtration here, so I will skip this one. And the main output of persistent homology is something called the persistence diagram. Okay, in practical situations, the parameter R that we're using here, the distance parameter, can be interpreted as a scale parameter. For this reason, when you read TDA articles, you will find the scale parameter used as well, in addition to the distance parameter. We alternate between scale and distance to refer to R. We mostly use the term distance and use epsilon or alpha to refer to the distance threshold in our articles. So filtration tracks the appearance of shapes along the distance threshold alpha, and the information gathered through filtration is stored in persistence diagrams. Persistence diagrams are two-dimensional outputs I will show in a second, where the birth and the date scales or parameters. This B means birth, and this D refers to that. So for each dimensional hole, persistence diagram keeps two information, when it is born and when it dies. And the persistence diagram looks something like this on the right. On the birth axis, you have alpha starting from, let's say, 0 and going to maximum. On the that axis, we also have starting from 0 and going to maximum. And the diagonal means the birth is equal to the that. For example, let's say this is alpha and this is the alpha. So it can happen that a dimensional hole is born and dies immediately. Or if it is born at X and if it dies later, it would be here. Okay, so this, let's say, alpha plus 0.5. In that sense, we will say this hole here, this specific one, survived for 0.5 long. Okay, because it was born at alpha, it dies at alpha plus 0.5. So that means if a hole is born and then it dies immediately, it will be closer to the diagonal line. If a hole is born and does not die, it will be very far away from the diagonal line. It will be here. If the hole never dies, it can be the case actually. For example, let's say this is the maximum and then there is the infinity, meaning that this hole does not die ever, how much ever you increase it. Okay, so here in this data point cloud on the left, we have actually 3 holes. This is the first dimensional hole. Let me clean the ink. Okay, this is the first dimensional hole. You will see that it's actually closer. It will die if this vertex and, for example, this data point creates an edge. For this reason, it dies sooner than the others. So it is, for example, lifetime is L1. Then we have the second one-dimensional hole, which is a loop here, and then you see it actually survives a little bit longer than the green one. Let's say this survives L1 plus alpha 1. And then the third one is the largest hole. It will survive the largest, so this will survive L1 plus alpha 1 plus alpha 2. By just looking at the persistence diagram, which is this one, we can understand which holes survive longer. Yeah. By definition, nothing can be on the lower diagonal because nothing can die before it is born. So there will be nothing here. It will be always on the diagonal or a bit far away from the diagonal. And this persistence diagram in this case is actually showing us one-dimensional holes. So this is a persistence diagram for one-dimensional holes. If you want to show other dimensions, we actually use different colors. For example, here, this one is green, red, and blue in color. If you want to show one-dimensional holes, we can show all of them as red, and then zero-dimensional holes can be shown as blue, for example. So on the same persistence diagram, we can see both zero-dimensional holes and one-dimensional holes. And here, this is coming from Mary's work, my PhD student. We do this. These red dimensional holes are zero holes, zero-dimensional holes, and the blue ones are one-dimensional holes. You see these one-dimensional holes along the diagonal, they die almost as soon as they are born, so they are not important. What we are interested in are these ones that persist for a long time. This is important. You see, zero-dimensional holes die, and then one of them does not die because it doesn't matter how big data point cloud you have. At the end, when everything is connected, your disconnected component is 1. So this one of these holes will survive forever. It does not die. This is why we have the infinity here. Yeah. So persistence diagram is a nice thing. However, we cannot really use it in machine learning because we need to vectorize it somehow. Like we need to put this into a vectorized information that says, for example, at alpha 0.5, there are 5 one-dimensional holes. In the next one, it has 6, and then most of them die, become 0, and then become 7. So we need a vector form to use in machine learning applications. And there are a few important ones. For example, one is called persistence silhouette that takes this information and creates this. And this is only for the one-dimensional holes, this persistence silhouette. We have persistence landscape that is also one-dimensional holes here. And in the third one, we have a barcode that we showed before. So this is the barcode. And the red ones are zero-dimensional holes, and the blue ones are one-dimensional holes. And you can see in the beginning how many zero-dimensional holes we had, 1, 2, 3, and so on, because there were like X data points. And all of them survive. And then here, many of them die. And then after some point, there's just one zero-dimensional hole. That means everything is connected. So Betty 0 is 1 here, Betty 0 is 1 here, and this is shown with this long line. That means one of the zero-dimensional holes does not die. Let's look at the one-dimensional hole. So we have a one-dimensional hole that is born here, another one here, and then another one here, and then eventually the top one dies because vertices get connected, but this one survives a bit longer. So this is the longer surviving one here. That is this hole. And we'll look at the persistence diagram. Zero-dimensional holes are born immediately, almost immediately, because the distances are almost the same between data point clouds. It's like they are uniform. You know, if there was another data point here that far, then one of these zero-dimensional holes would be born, let's say, around here, because this distance is high, so it will take this much to be born. Yeah. So to summarize, we have covered TDA basics, which are defined over data point clouds. And here is a pseudocode for computing persistent homology. We get the vectorized pH output, and then we will use the vectorization in machine learning tasks. These are the main points in applying pH to point clouds. I will stop here, and if any questions, I will take them, because topological data analysis on graphs will be our topic for the next class on Wednesday.
Okay, thank you very much. Is there any question? If you have any question, you can, yeah, okay, thank you, Navid. And you can raise your hand, and also you can write in the chat box. So wait, now you can talk, Navid. Yeah? No. Hello? Hello? We cannot hear you. Can you maybe write in the chat box? Maybe you can try later.
Yes, I believe that there will be like more interesting points when we are talking about graphs, because I will be presenting our papers, and it will have more questionable things, let's say, choices and metrics and so on.
I have one question regarding the application of topological data analysis to machine learning, because one of the things that the computation of, for example, persistent homology in a big data is that feasible? Is that, for example, like comparable to training a neural network with a very big data? Is that you need more time, fewer time? Is that comparable? Do you know what I mean? How is
Yes.
the experimentally? I know theoretically that it is cubic, but experimentally, because I know you use a very big data. So is feasible to use topological data analysis in a data very big?
Yes. So the computational complexity is something that I avoided because I'm going to talk about it in the third day. We have a paper on scaling TDA to graphs. But in general, the computational complexity of persistent homology is ON cubed,
Yeah.
and where N is the number of simplexes in your data.
Yeah.
So that means actually it is quite costly. And for this reason, persistent homology is not applied to, let's say, 1 million node graphs. Okay, so it is not applied to very large graphs. The same limitations are shared with graph neural network methods. In graph neural networks, we have, for example, GraphSage and others that are doing sampling on the graph so that GNNs can work on large graphs. PH has this problem. However, consider that the computational complexity of persistent homology increases when you look at bigger than 2-dimensional holes. So if you just look at 0 and 1-dimensional holes, and sometimes maybe the second dimensions, these are not very difficult to capture. Yeah. So 0 and 1-dimensional, we can do a bit large graphs. And in the last 2-3 years, we have seen algorithms from computer scientists that scale up, because TDA is used by mathematicians, which are not mainly interested in computational complexity.
Yeah.
But computer scientists have brought down the computational complexity lower. And this n cube is actually something similar to 2.36, I believe. So it's not n cube, but n to the power of 2.36 or something. The main difficulty comes from finding the rank of a homology group.
Yeah.
This is why it is difficult.
Yeah. So as far as you know, only 0 and 1-dimensional persistent homology is used in machine learning tasks, right?
Yes, because we looked at 2-dimensional holes as well, but in most data sets we don't have them. For example, we are looking at molecular graphs. There are no 2-dimensional holes. We are looking at social network graphs only on Facebook and Twitter. We found them. We did not find them on other graphs.
Okay. Okay. And regarding the input data, because you talk that the input data is a finite collection of points. If we have, for example, images, you don't consider the image like a vector, I imagine, or yes. How do you proceed? How do you go from the images to from a data set of images to a data set of points? How do you do this, or do you know how people do it?
There are actually a lot of articles on using persistent homology on image data. In image data, they consider each pixel as a data point, and then define distances based on, for example, color similarities or something.
Okay. Okay. Okay.
Yes. There are articles. There are very interesting articles on using images, because on images we have these 1-dimensional holes, let's say, and PH can find them.
Okay. Okay. Maybe now. Okay. Now you can talk now, Nabil. Try, please. No? Hello?
Hello, Susanna. Hello, Rothio.
Hello, we hear you
Hello,
now.
how
Yes.
are you? I'm fine.
Fine.
And you?
Fine.
First of all, I thank you, Rothio, for your supervision for me, and I thank my brother for this presentation. I have a question about this axis of research. It is possible?
You mean to give your presentation now?
I have question.
Question. Yes, of course. Yes, please.
The impact of or the value of topological information to describe the problem of the big data. Can you explain this? Explain the method with like in field like economics, like biology. I want an example to explain the topological information in the big data.
What is the type of the data in big data? There can be large text, there can be documents, there can be image or video. So what is the data type?
In time series, or in you agree with me? The application of topological information in the field of the big data. The big data is uncontrolled, so I don't.
Okay, I lost Nabil's voice.
Yeah, I think so. We lost you. We don't hear you now. I'm sorry.
Yes, but in terms of big data, I can say that TDA, I have not seen it. I mean, I'm sure that there are some works, but I have not read any papers applying TDA in, for example, real-time streaming video, for example. But in the future, I'm sure we will have something, because TDA is now being scaled. Researchers like me are developing algorithms to apply TDA to larger graphs, larger data sets, images, and so on. So it's just a matter of time before we have a breakthrough, actually. So I believe that our work that we presented in University last year was a breakthrough in computing person homology on large graphs. But graphs have some certain things that we use to our advantage. In data point clouds, still I have not seen, let's say, a data point cloud of 100 dimensions and so on. I have not seen it using TDA. There are some methods like alpha complexes and so on that says we can do scalable person homology on large data, but when we use them, we found a lot of issues with them. For example, in graphs, you need to have connected graphs, which may not always be the case. So my student actually had so many issues with alpha complexes, we kind of stopped using them. So I'm sure we will develop some methods. It's just a matter of time. I'm very optimistic in that.
Okay, so any other question?
I will stop sharing and maybe my video will work and students can see me as well. It's important because then if you see me in a conference or something, you could come to me. Oh, I see the point. The problem is that, yeah, wait. Okay, I think now you will see.
Oh, but you have to mute maybe this one. Eva? No. Maybe me.
Okay. Okay, now it should be fixed. I was trying to get out of Safari. Yeah, so that is it for today. Tomorrow and the day after tomorrow, let's say Wednesday and Friday, we will have quite interesting applications on blockchain graphs as well. So I hope you can join us. Rocio, can you hear me? Yeah.
Yeah, I can hear you.
Yeah. Okay. Thank you very much, everyone. And talk to you on Wednesday.